Good afternoon, everyone. Today we'll be talking about enabling precise optimizations in just-in-time compilers without sacrificing this efficiency. You can read it the other way as well. Making just-in-time compilers or keeping just-in-time compilers efficient while increasing the precision of the optimizations performed therein. So we would be basically trying to balance both of them. I am sure many of you would find several interesting novel things here, and please feel free to interrupt me, ask questions at any point of time. All right, so what's this logo? This is Java. So let's start. Well, just-in-time compilers are there in many languages now, but Java was one of the forefront languages that brought their usage to the real world per se. So we'll talk about what's special about Java to begin with in general without any JIT compilers and so on. So first of all, the reason Java became popular in the 1990s, one of the main reasons was platform independence. Internet was getting popular. People wanted to write Java applications on a particular machine and be able to run them anywhere. Phones, desktops, clouds, browsers, and so on. So platform independence with this abstraction of the Java virtual machine, where you have bytecodes, you run it on a VM installed on any different platform, was one of the first reasons for Java's specialties. Then one of the other strong things or other positive things about Java is a strong static type nature. So invalid operations are disallowed by the compiler, which means happy users. Once you ship a program, it's unlikely to fail. Java's type system is stronger than C and C++'s, for example, which were contemporary popular languages at that time. Well, Java won't throw sec faults on your face, unlike many other programming languages. Instead of that, it would tell you where did the exception get precisely thrown, along with a complete stack trace that tells where did you reach there, from which call to which call to which call, and so on. So developers very often don't need to struggle with debugging in Java, or even the debugging experience is simpler in Java, arguably, than many other languages. One of the most liberating things, on the other hand, is automatic memory deallocation. You can just keep allocating memory. You never have to worry about when to free up a particular piece of memory, when to insert a delete instruction or a free statement, and so on. You don't need to bother about memory deallocation. There is an automatic, or there is a garbage collector thread that would automatically free up unreachable memory for you. That liberates programmers, and I'm sure anybody who has written programs in languages which do not have automatic memory deallocation, and when they shift over to Java, they really find it liberating. I did, for example. So these are good things about Java. Now let's talk about what's problematic about Java. Okay. The first good thing was platform independence, but well, platform independence makes optimization difficult, isn't it? Java C, which is the high-level static Java compiler that converts Java code to bytecode, it cannot perform any machine-dependent optimizations because the code is platform independent. It's very simple. It's basically written for a stack machine, not for the actual hardware. We said strong static typing is good, but then it means that people in LLVM social who are very much very much proficient at directly talking to the memory and improving their programs. In Java, you can't touch addresses directly. You can't manipulate addresses. You have pointers, you have references, but you can't really do anything with them except that access the memory pointed to by the pointer. We said exceptions with stack traces are good, but this how do you even print the stack trace, right? It requires a lot of symbol and state tracking. You need to remember line numbers. You need to be able to reconstruct or at least print the whole stack and so on. So again, there is overhead. You're running a program and you have to worry about a lot of this meta computation in order to ensure that you are able to throw these nice exceptions to the programmer. And automatic memory deallocation is very complex, you know. And these garbage collectors, even though we said it will all be automatic, but they are threads that are running in parallel with your program. They snatch resources from the program. Even now, many people might notice when you run a Java application for a long amount of time, you may experience pauses, and those pauses are nothing but GC stopping your program in order to stop the panic that's probably about to happen due to lack of memory. Okay. So these are problems about Java as well. So of course, let's summarize it this way: Java is nice, but there is a cost associated with it. There are lots of costs associated with it, as we can see on this slide. But then Java programs don't run slow anymore, even though we have so many costs at runtime. We are maintaining so much of extra information. We have parallel threads doing their job along with our program. But Java is no longer a slow programming language as it was when it was invented in the early 90s. Right? The reason is, of course, many of you are familiar with just-in-time compilers. So Java bytecodes nowadays, apart from interpretation by a stack machine for which they are emitted, they are compiled just in time to native code in the JVM. And these just-in-time compilers are not very specific to Java, of course, as I said in the beginning as well. There are many programming languages which have these JIT compilers, and JIT compilers optimize your code for a particular hardware, so they can do machine-dependent optimizations, as well as they can optimize your code based on the runtime profile of your program, and all this kind of gives performance to Java programs. In general, more the dynamism in a language, right? More the number of things you cannot determine statically, less is what a static compiler would be able to do, and a JIT compiler optimizes those programs written in those languages more successfully. So in fact, Java is, with the sophisticated just-in-time infrastructure that has come to the Java world over the last 2 decades, it's now even used to write complex software like compilers themselves. For example, Oracle's Graal JIT compiler, which is shipped along with the hotspot VM that you might have on your machine, it's written in Java. Okay? And it now outperforms the good old C2 compiler written in C++ for almost all the scenarios. How about it? Nobody imagined that you would write a compiler in, well, we had Dragon Book's version, the recent version of Dragon Book explains everything in Java because of other features, design patterns, and so on. But then Java code can now be used to write efficient compilers. And Oracle, for example, is pushing the Graal compiler instead of the C2 compiler. Might happen that it replaces it completely in the near future. That's interesting. Let's understand first, how does JIT compilation work in the hotspot VM? Of course, as I said, it's not specific just to Java. And in Java itself, in the Java land as well, there are many other virtual machines. The OpenGenine virtual machine, we'll talk about it a bit later. There is Graal's VM as well. And then you have the hotspot VM, which is the most popular Oracle shipped industry virtual machine that most of us use. Okay. What happens is, we have our main program, right? We have our main class with a main method in Java. So when I shift this bytecodes to the machine on which I want to run my Java program, basically the VM starts with interpretation of bytecodes. It starts very simple. It just interprets in its stack machine in the model of stack. You have push pop instructions in the bytecode, and it starts with interpreting these bytecodes one by one. Okay, simple. However, while interpreting the bytecodes, it also does some profiling. It, for example, identifies how many times a particular method is invoked. It just keeps counting for each method in your program. It keeps counting how many times you traverse a package in a control flow graph. Or rather, simpler words, it tells you how many times is a loop iterated over and so on. So loops, methods, sometimes even other parts of the program, traces, and so on. So there is this profiling done while interpreting your bytecode in the JVM. And now, once you identify that some code region, let's say a method is hot. By hot, we mean it's executed frequently. Let's say above a threshold, above 10,000. If a method is called more than 10,000 number of times, well, why am I interpreting that method and spending a lot of time? It's a hot method. Let me optimize it in a JIT compiler. That's the idea here. So once we identify code regions that are frequently executed with this basic profiling information, these hot regions of the code are inserted into a compilation queue. So there is a compiler, or there could be multiple compilers sitting as threads waiting for some job to compile. Now these compiler threads will pick up items, pick up methods or loops or code regions and so on from their queue, compile those in the background while your VM has not stopped. It's continuing to interpret your remaining program. Okay. Now what happens is, let's say I found that a method foo got executed frequently, and hence I sent it to the compiler while I'm interpreting the method foo still. Next time the method foo is called, if the JIT compiler has finished its job, if its JIT compiler has given me an optimized binary for foo, I would change the entry point dynamically. Next time somebody calls foo, I would switch the entry points as I oh, you don't need to go to the interpreter, you can directly execute this native code that has been generated by the JIT compiler. Similarly, hot loops can be replaced on the stack. While being inside the stack frame of a method, you can jump to, you can change the entry point of the next iteration of a loop to compile code. This whole jumping from interpreter to compiler as well as coming back from compiler to interpreter, we'll see why the second one can happen. This is called on-stack replacement. And just because I have a very good audience here, I just tell that this OSR has a very beautiful engineering involved. Okay? In order to be able to jump from or switch context from one code execution environment to another, from a stack machine to the Intel hardware on your actual machine, or let's say the other way around, you need to maintain a lot of state information. And you need to be able to copy the values of registers from one place to another, copy the values of the stack top in this case. You need to be able to store the state, restore the state to a certain point from which you can continue execution in a completely different environment. So that's also going on while your program executes inside a JVM. Yeah. So basically in the hotspot VM, there are multiple tiers like this. Okay. So first, your code starts with interpretation, as I mentioned, which is level 0. Interpretation with some profiling like counting the number of times a method is called. Then there is one C1 compiler or the client compiler. There are two JIT compilers in the hotspot VM. The first one is C1, the second is C2. So pure C1 means, okay, if let's say you cross a particular method's number of times it's executed crosses the C1 compiler threshold, it's sent to the C1 compiler. After some time, let's say it's getting executed again and again. You might want to start some profiling in C1 as well. At some point of time, you might say, let me send it to a more powerful compiler. Like in GCC, you have a 01, 02, 03. You might say, okay, this method is being called even more frequently, or you may profile some more information and find this method has potential further optimization opportunities. Let me send it to a better compiler, more powerful compiler. So that compiler may spend a bit more time JIT compiling the code again, but it might implement optimizations that are powerful. It may have loop optimizations instead of a simple linear scan register allocator. It may have a graph coloring based register allocator. It may have memory related optimizations and so on. Okay. So finally, at some point of time, if a code is very hot, you may switch over to C2. What it means is, next time you're calling that code, if C2 code is available, you might switch to the C2 version instead of the C1 version. Right? So we usually, when we see program executions in a VM, we can observe some sequences. For example, your code might be interpreted, then it might directly be sent to level 3. After that, it may go to level 4. It's also possible that okay, the level 3 compiler is busy, its queue is nearly full. Let me directly send it to the level 4 compiler whose thread is sitting idle. And then we have the third row in the figure here, where what I show is after going to a certain compilation level, you may also come down. You may come down to a colder path. You might say, okay, let me switch over back to the interpreter, or let me switch over back from C2 to C1. We'll see why this downgrading of the code can happen as well. Okay, so basically the idea of this slide is you have multiple levels of compilation along with interpretation in the JVM, and your code is traveling across these levels while being executed in the VM, which gives it performance. We'll see one very powerful way JIT compilers give performance compared to, let's say, AOT compilers, which is using speculation. So I'll show a lot of code today. I'm sure all of you like code, so we all are in the same boat. Let us focus on this method on your left top side. There is a method foo that takes two parameters, an integer parameter a and another parameter o, which is of some type x. I show x arrow, y arrow, z. That notation simply means, let's assume I have three classes in my program. X is extended by y, so y is a subclass of x, and z extends y, so z is a subclass of x. Okay. Now each of these classes X, Y, and Z define a method bar. Different versions of this bar method do different things. So the X copy returns 5, the Y version returns 2, and the Z version returns 10. In the method foo, I'm calling o.bar. So this is a virtual call. All calls in Java are virtual, which by default virtual. So what it means is when I say o.bar, the actual method bar will be to be called will be determined at runtime based on the type of the object which is pointed to by O at that point. Since the static type of O is X type or Y type or Z type, any of those objects can be pointed to by O. Depending on what object is being pointed to by O in a certain execution of foo, the right bar method will be called. So this is my code. Now I am JIT compiling only foo. I don't know from where foo is called. I don't know the call sites of foo. Only this foo was a hot method that was sent to me as a JIT compiler, and I have to compile this method. Now let us say, well, I was doing basic profiling like method invocation counts and loop iteration counts and so on. Let me also profile more interesting information. We saw this, if you go back, you saw this level 3, right? Where we said even with full profiling. What is this full profiling? It's more than just counting the number of times something is called. So let's say while I counted information about the values of parameters, I found that most of the times, let's say 95% of the times foo has been executed in the past, I found that A's value is always 10. Okay? If I see that, I can probably speculate that A is always going to be 10. So let us say this comment, let's say assumes or mentions an assertion here or an assumption here. It's assuming that A is 10. If A is 10, I can constant propagate A. I could fold the expression A plus 10 and B can be replaced by 10. I have removed the variable B and B has become 20, sorry, not 10. So the second statement is in C equals 20 times O dot bar now. If I could profile the value of A, I could also profile the type of O. Why not? So let us say I find that most of the times the method foo was called, the object pointed to by O was of type Y. X objects can point to X, Y, or X variables can point to X, Y, or Z objects, and I found most of the times it is Y. If it is Y, I could inline the under this assumption that it's Y, O's type is object pointed to by O, that type is Y, I can inline Y dot bar, which means I could say return 2, which means int C is 20 times 2. Now I can perform more constant propagation under these two assumptions. I can say I can remove these variables A, B, C, all of B and C, both of them all together. I could just say return 40 after performing some more constant propagation and folding. Okay. Finally, after performing these optimizations, these speculative optimizations, the JIT compiler's code generation phase will give an equivalent assembly. Now, what is the equivalent assembly? The assembly, the version of foo that I have right now just returns 40. It doesn't do a vtable lookup to find out which method is called. It doesn't perform addition. It doesn't perform multiplication. It doesn't do a method call altogether. It just returns 40. Okay, this is what is my assembly. I perform many more optimizations under a guard. This is called guard in JIT parlance. So the guard here is A equals 10 and type of the object pointed to by O is Y. So under this guard, I have an optimized assembly generated by the JIT compiler for this original method foo. Of course, you all might get this question. If we compiled and created a specialized binary, specialized for those two particular kinds of arguments, under the assumption that we have noted down, now we are dispatching to this binary whenever there is a call made to foo in the VM. Now, what if one of these or both of these assumptions fail in a subsequent run? Next time I call foo, I don't pass 10, I pass 20. What do? I cannot use this equivalent assembly. Let's assume assemblies look like pentagon. So I cannot use this assembly pentagon generated for foo. Right? It's in pentagon or hex. No, pentagon. So I cannot use this binary basically. I need to fall back to a path or to a version of foo that did not make the violated assumption. This phenomenon is called de-optimization in Java virtual machines. De-optimize because you had optimized under certain assumptions. Now you have to de-optimize and go back. So let's JITs perform all these speculation and
Sorry, Professor. Sorry to interrupt. So when you mean
yes,
de-optimize, you store one version of the optimized foo, right? You still have the interpreted version of foo,
correct,
right?
correct,
So you
correct. So
do you have to de-optimize, or I'm not sure what do you mean by de-optimization here?
sure, de-optimization just means next time you call foo, if the assumption is violated, you will fall back to some code which did not make that assumption, which could direct, as you rightly said, it could just mean interpreting the code again. Or if let us say I had one more version of foo where I had not made that assumption, I made some other assumption which is true, I can pick up and use that version of foo. Make sense?
Okay. Oh, yeah. Thank you.
So this phenomenon is called de-optimization in this space. All right. So all this is good, but then speculation and de-optimization have, of course, their overheads. But there is a big thing that's missing here. In fact, I was listening to another talk given some time ago on this channel, and I found somebody even mentioned about JITs having a lot of complexity. I think it was Saurav's talk. So the biggest problem about JITs is that time spent in JIT compilation directly affects the execution time of the program. So whatever we are doing during JIT compilation is happening while your program is actually under execution. Okay? So speculation and de-optimization aside, most JITs by default perform very imprecise program analysis. By imprecise, I mean let's say only intra-procedural, no inter-procedural analysis in the JIT world. Sorry, they lose opportunities for optimization. You might, for example, ask, so many optimizations are there in GCC to perform flow sensitive analysis and so on. Now, all of it, will you find them in a JIT compiler? Most of the times, no, which is so unfortunate given the popularity of JITs nowadays, right? So one of the questions that I asked, that my team started asking around 10 years ago was how to bring decades of advancements in static program analysis to the JIT world. This was the question we tried to answer, and that gives rise to this. The title of the talk, that this is our seesaw, precision versus efficiency. Precision and efficiency are always at the other ends of the spectrum, or most of the times at the other ends of the spectrum, but in JITs the effect is even more pronounced. You really don't have budget to perform precise program analysis in order to maintain efficiency of execution. Okay,
Uh,
so
so, Professor,
yes.
sorry, there's a question in the chat. So, Srijan asked, we
Uh-huh.
have to assert the param guards every time the function is called. Does
Mhm.
it mean that non-JITed code paths end up being slower on average?
So there is a contradiction in the questions region. When you assert the param guards, well, not only param, you can have any other guards, anything about the state. When you assert these guards, you are in JITed code. Okay? It's not non-JITed. So if I assume your question is JITed code slow because of these guards? The answer is most of the times no, because you would have optimized the code further with these guards. Okay?
No,
Non-JITed code
so
path you can enter without any param guard check.
no, no. My question was every time you call these functions,
Mhm.
regardless of whether the implementation is JIT or not, every time you call this function, you have to verify that the parameters have the types or the hold the invariants that we expect them to before we
No,
can.
right? If I have non-JITed code, that code did not make any speculative optimization. So if my entry point is the interpreter or a version of the compiled code which did not make any assumptions on parameters, let's say the C1 compiler does not perform speculation. So if I have interpreter, if my entry point is to the interpreter or to a C1 compiled code, I never need to make any check. Make sense?
Right. Yeah.
Uh,
There's
Ramneet.
another question. Yeah.
Yes, Ramneet asked, could AOT compilers also make similar? Well, let's take the question about AOT at the end. Okay? We'll talk about JITs right now, just to maintain the flow. I'll take your question, Ramneet, at the end. All right. So, as I said, we would like to balance this precision efficiency trade-off. And for today's talk, let's concentrate on object allocation, access, as well as deallocation. The most prominent thing associated with an object-oriented program is an object. So let's talk about how do we optimize operations involving objects, which include all of allocation, access, and deallocation. So let us assume in this piece of code that an object allocated, I'm calling it abstract object because same code can be executed multiple number of times. So let's say an object allocated at line number L is denoted as OL. Under this notation, the method foo here allocates three objects, O4, O5, and O6 at line numbers 4, 5, and 6 respectively. Okay. In Java, you allocate objects using the new keyword. So there are these three allocation sites in this method foo. And you have an assignment to the variable g at line number 10, which is a static field, okay, static dg, as you see at line number 2. So any static field in Java is like a global variable, just pointing it out, in the sense that anything that's reachable from a global variable can be accessed by multiple threads. So if something is pointed to by g in this case, that object can be accessed outside the method. It can be accessed through the global variable. It can also be accessed through other threads. And as we know, all the objects in Java are by default allocated on the heap. Garbage collector clears out unused objects periodically. It keeps running at certain points of time. There are also concurrent GCs and so on. So garbage collection has its overheads, as we mentioned. On the other hand, memory allocated on the activation record or stack frame of a method, like the local variables, that memory gets freed automatically after method execution. Right? You pop off the stack frame of a method foo, everything that was local to foo, allocated on the stack frame of foo, just gets freed away. Further, accesses on stack are more efficient than those on heap. You can replace them, let's say, with constant offsets instead of making indirections multiple times on the heap. So that's the comparison between stack and heap. So the question here is, well, by default, everything is on the heap. Every object is on the heap. Can we allocate some objects at least on the stack? Because if we allocate them on the stack, the access of their fields is faster, number one. Number two, their deallocation is free. You don't need to do any garbage collection specifically for that object. So the analysis that allows us to determine method local objects, the objects that are local to a method and hence can be allocated on the stack frame of a method, the corresponding program analysis is usually called escape analysis. Okay? So an object is set to escape its method of allocation if it can outlive the activation record of that method. Let's most of you might be familiar with points to analysis. Points to analysis just says which variable might point to which objects at runtime, or which field of which objects may point to which other objects at runtime. Okay. In Java, if you perform points to analysis, let's say we are performing pointer analysis here, we'll get points to sets. Since I'm performing the analysis statically, a variable may be determined to be pointing to multiple objects, since it's a may points to set. So X in this program may point to O4. The points to set of Y has O5 because of line number 5. O4.F points to O6 because of line number 6. And the variable G points to O6 because of line number 10. Clear? So these are the points to sets. Now, based on these points to sets, we can determine that O4 and O5 are reachable only from a local variable, X and Y for each of them. So they do not escape the method foo. On the other hand, O6 is you see line number 7, I say bar X, which means X was pointing to O4, O4 is passed to bar, and there in bar I do G equals P dot F, X was P, so P dot F is O6, so G points to O6. G is a global variable here, or a static field rather, hence we say that O6 escapes at line 10. Determining this requires a lot of analysis though. This was a simple piece of code, but capturing O5, capturing means identifying that O5 does not escape. It requires an intra-procedural reachability analysis, usually performed using a points to graph. Excuse me. So you need to maintain some data structures, perform some pointer analysis, and determine that, okay, O5 does not escape the scope. Capturing O4 requires an inter-procedural analysis, right? O4 is passed to bar via the argument X. And in order to find out whether bar lets this escape by assigning, say, to a global variable or doing something else mischievous, I need to perform inter-procedural analysis. And similarly, in order to find that O6 does not escape until line 10, requires performing a flow-sensitive analysis. These are analyses that are not heard of in the JIT world, unfortunately, as I said. Okay. So what would an escape analysis in existing JIT compilers do? Since you don't have time to perform complex analysis, you would probably just perform, let's say, intra-procedural flow-insensitive analysis. So for example, hotspot and OpenJ9's JIT compilers can stack allocate O5. If they perform intra-procedural analysis, okay, O5 is local, it doesn't go anywhere, fine. I can stack allocate it on the activation record of foo. And sometimes O4. If let us say in the runtime inlined bar, if it inlined bar, then okay, I can without an interprocedural analysis determine that bar does not go out of O4 does not go out of scope. Okay. And then sometimes these JIT compilers can stack allocate O4 in our example here. Okay. So now the claim here is that JIT analysis, the precision of JIT analysis is usually very poor, sometimes enhanced by speculation and so on, which can allow you to perform more method inlining than you can do statically. However, the opportunity that lies here is that, well, Java programs are available statically as well. I have a Java C static compiler as well. So program analysis can be performed statically either on Java source code or Java bytecode, as well as during JIT compilation. I have two opportunities. I have an opportunity here to get a lot of benefit of AOT compilation as part of Java C, let us say, as well as I have a lot of, I already have advantages of speculation and runtime profiles and whatnot inside the wheel. Okay? So let's use this opportunity. This was our solution to begin with. Okay? So what we did was we had a work called as the PI framework. PI stands for precise yet efficient in 2019, where we said, okay, let's perform static analysis for Java, ahead of time analysis for Java as much as possible. Now there are constraints like in languages like Java, your Java libraries, their source code is not available. You can link a different version of the library and run your program in a VM compared to what version you had assumed on your machine where you actually wrote the program. So which means I cannot perform whole program analysis statically. That was a big challenge. So we said, well, we can analyze applications and libraries independently. We did it in the suit static analysis framework. And then we merge these results during JIT compilation. Let's say I pass an object to a library method, I don't know what happens inside. So instead of saying it escapes, I would assume that, okay, I will remember that, okay, I have passed it to this particular library method. Let me resolve the dependence on that library method in the JIT. Okay. So this was something we did in 2019, where we were able to, we came up with an approach to use the results of precise static analysis for enabling sophisticated optimizations in the JVM without much JIT cost. In the JIT, we disabled all the analysis. We said, okay, you can use these analysis results from static analysis time, and now you just do the marriage of results, which is faster than performing interprocedural analysis, data flow analysis, and so on in the JIT. And we thus get more precision than what was possible inside a JIT compiler earlier. Now, I'll speed up a bit from here, having built the background. So if I decided to use this idea of performing static analysis as good as possible and using it in the VM, I could have performed, so if I wanted to use this idea for stack allocation, I could have performed precise analysis over Java bytecode using suit. And let's say I store the results in some files or as annotations in my Java bytecode. I use these analysis results to perform stack allocation of a possibly much larger number of objects using JIT compilation. Right? It would have been just very straightforward. But there are few big hindrances. Okay? For example, now if you are performing static analysis over bytecode, in the VM you have JIT, and then JIT has its own IRs, multiple IRs in fact. Okay, right? So the results computed statically should actually make sense during when you actually decide to perform stack allocation inside the JIT. Okay? It may happen that you said object at line number 10 can be stack allocated. In the VM, when the JIT performs stack allocation passes, there is nothing like line number 10. Source code doesn't exist. Line numbers, let's say, don't exist, and so on. Okay? So just giving an example. So the environment has changed. Your static analysis results might have become unusable. That's one challenge. The second challenge is languages like Java have a lot of dynamism. They allow things to change at runtime from what you expected statically. For example, you can callback. You can make a callback from library to the application. So you have an edge in the call graph that was not known statically. You may load a new class dynamically, which was not available to you statically. New class means new code can be called, new methods can be called, something different can happen. They also have features like hot code replacement. So in a debugging session, you can just change any line of code. Now, if you have performed some optimization based on static analysis results, what do you do? Okay. So, well, the first problem is a bit simpler. It was not so simple from an engineering perspective, but it's simpler at a conceptual level. We said instead of source code, we would analyze bytecode. And in bytecode, instead of line numbers, we have these bytecode offsets in the Java class files. So, for example, a new is translated to the sequence of bytecode shown to you on the right hand side. We said if you want to use static analysis this way, you could represent escape analysis results in terms of bytecode indices. Similarly, if you are computing some information about variables, you can represent that information in terms of the stack slots those variables are supposed to be in. All that information is present in the class files, as well as it's present initially in the VM. So the challenge here, as I said, is you need to preserve this information, and once the VM is translating your Java bytecode to some other IR, you need to translate this information from whatever analysis information you've computed from bytecode to that IR and the next IR and so on until that information can be used to perform a particular optimization. In fact, Suite does not directly support BCI starting JDK8, so we had to extend Suite along with its front end. As I said, a lot of engineering was there to preserve BCIs in the class files themselves, to obtain correct BCIs and preserve them. So we solved this problem with all this engineering effort. But the more interesting one is the second problem, dynamism. So we said static analysis often cannot capture possible dynamic features that could happen, and hence static analysis results might go wrong. In this case, it may lead to incorrect stack allocation. Is there any question? I thought somebody said something.
Oh no, Professor, there weren't any questions.
Okay, let's go ahead. So static analysis results might go wrong and lead to incorrect stack allocation or any other wrong optimization, right? Let's consider an example. Here we have a method do. So I'll tell you where to look at. Here we have a method do at line number 5, 6, and 7. You have three objects: 06, 05, 06, 07. You have another object at 09. You call some methods zar and bar and so on. Okay. So now if you do flow sensitive interprocedural escape analysis here, you would find that objects 05, 06, 07, 09, all of them can be allocated on the stack frame of do. None of them is actually outliving the scope of do. Okay. However, so yes, there is a question. Please go ahead. Somebody raised their hand. By mistake. So let's say using the static analysis, I decide to allocate objects 05 to 09 on the stack frame of do. Okay. I have allocated them in the VM while doing JIT-compilation and so on. Now I use this feature called as HCR. While running the program, let's say the programmer replaces q.f is equal to new a at line 14 with q.f is equal to p. Now what happens? If the statement is q.f equal to p, the object pointed to by p is stored into the field f of the object pointed to by q. P was pointing, let's come back to do. P was pointing to whatever a.f was pointing to, which was 07. So now 07 is stored into the field f of q, which was a parameter taken by do, which means q was pointing to some object which was allocated by some caller of do. That object's lifetime is longer than the lifetime of do. If I store 07 into a field of that object, then 07's lifetime is also longer than that of do. If I have stack allocated 07 on do, as soon as do stack frame gets popped off, 07 goes away. I may get an invalid memory access. I may get a sec fault in Java code if I do not do something, if I let this happen. So there is a problem here. So if we use static analysis results, these dynamic features may make our static analysis results go wrong, and the VM may crash, or missile may get fired, anything may happen. Okay. So similarly, since 07, one of the fields of 07 was pointing to 09, 09 is also incorrectly on the stack. Okay. So now, because of this reason, a pessimistic person might just say, pessimist might just say, do not use static analysis results in a VM. In fact, that's one of the reasons static analysis was not used to improve JIT compiler optimizations for a long period of time over so many decades. Okay. However, we say, well, in JIT compiler writers are very familiar with speculating, de-optimizing, invalidating, falling back, changing the code version, and so on. Why not use the same logic for using static analysis results? This was an insight that we adopted here. And what did we say is, let us treat static analysis results as hints to perform optimistic stack allocation. Let's just call our stack allocation with static analysis results optimistic or speculative, and then detect and repair incorrect stack allocation dynamically. Okay? We should have a mechanism that can detect if some stack allocation was incorrect and repair things such that that missile doesn't get fired. Okay? So let's see, how can we do that? So remember the idea, we want to detect at runtime if we have stored a non-local object wrongly on the stack. Right? In this case, when the detection happens, if you see on the right hand side, objects 07 and 09 were on the stack of stack frame of do, and P was pointing to 07. The variable P was pointing to 07. If I want to correct the situation, I can heapify. Let's use a new word here. I can heapify the object 07, which means copying the object along with its contents on the heap instead of on the stack. Let me move 07 on the stack. Then I will also make the pointer P point to not 07 on the stack, but 07 on the heap. Similarly, let me also move 09 on the heap. The G field of 07 on the heap should point to 09. So let's perform this heapification. This is actually a recursive heapification, because if something is pointing to another object which was allocated on the stack, now that thing also has to be heapified and its pointees further and so on. So this heapification is recursive, as well as we need to correct the references pointing to that object. Okay. How do we do that? How do we perform this heapification? This requires modifying the code gen routines of the interpreter as well as all the JIT compilers. You may have JIT compiled code in let's say the compiler C2, but references to objects created in the JIT compiled code might be in the interpreter or in some other compiled code, some other method's body, and so on. Okay, so we need to modify the code gen routines of all these execution, the code generators rather, and we should perform heapification over there. Okay. If we have this approach, static analysis results can be safely used until they are applicable in the JIT compiler. So now let's get to the heart of the problem here. Okay. If I want to perform this heapification, I need to detect when to perform heapification. Right? These, let's call them heapification checks. I need to perform these heapification checks at runtime. Is this object wrongly on the stack? Yes, then heapify. Is this object? So these checks are being inserted in the code generated by the compiler as well as in the interpreter, which leads to a performance problem. And these checks are frequent. In a language like Java, you need to perform this check at any statement that can make an object escape. At a store statement, you might be storing an object wrongly into some longer lifetime objects field and so on. So store statement, you need to check this. At a return statement, at a throw statement, basically at each possible escape point. Right? So let's concentrate at store statement for now. Let's say I have a store statement a.f equals b in my Java program. Assume a points to an object OA and b points to an object OB. This points to sets. So now, what is my heapification check which is there in the code generated for the store statement? If OB, the right-hand side object, is on the stack, if it is on the heap already, then nothing is problematic. If right-hand side object is on the stack, then if the left-hand side object is on the heap, then heapify the objects, all the objects reachable from B, OB as well as its fields and so on. Okay. This is okay. This is still just one more check on OA. But if both are on the current stack frame, then no problem, do nothing. The third case is more interesting. Both OA and OB are not on the current stack frame, which means OA can be allocated somewhere up in the call chain. Now, if we have to walk the stacks, I have to go up the call chain and find out if OA's lifetime was longer than OB's lifetime, then OB needs to be heapified. It's incorrectly kept on the stack. If OA's lifetime is same or less than the lifetime of OB, then it's okay. OB is stored to a smaller lifetime object, and hence keeping it on the stack is okay. right? So let me just illustrate this. I have a store statement a dot f is equal to b inside a method m3. I am inside m3. I'm executing this method m3. I have encountered a store statement. Now, none of the objects OA and OB are inside M3. They are not allocated in M3. They are not inside the address range of my stack frame, current stack frame. So uh, they could either be in one of the caller stack frame. Let's say O and OB both are allocated on M2 stack frame, which means I don't need to do anything. OB doesn't escape. But let's say I go up my call stack and find that OA is allocated in M2, but I did not find OB. OB is somewhere up. Then also I don't need to do anything. I can just continue execution. However, if I find OB first, OB is, let's say, on M2 stack frame and OA is on M1 stack frame. This is a scenario where I'm storing a shorter lifetime object into a longer lifetime objects fields, and hence I need to heapify, right? So these are the checks that I need to do. I'm sure everybody is starting to panic now. How come this just a store statement is being made so complex? Right? So much of stack walking, going up the stacks, checking things, address ranges, this, that, my program will get slower. I was trying to get advantages of stack allocation. All right. So here lies a key insight of our work. The last two cases, right? If OA is on a stack frame that is popped before OBs or after OBs, if my stack, let's say, is growing downward towards lower addresses, I can just do address of OA less than equal to address of OB. I still insert a check, but only a simple address check. If this condition is true, that means I don't need to do anything. Okay? The trouble is the last one. I am executing a dot f equal to b. I don't know where are OA and OB allocated, and what if they were on the same stack frame? Okay? It's a do nothing case, but I will have to actually walk the stacks and find that out. So the question we asked was, when will address OA less than equals address OB be a sufficient check even in the first case? Okay? It would be a sufficient check if somehow OB was placed on the stack before OA, so that before means on a higher address inside the same stack frame, OB has a higher address than OA, which means this check will just do the purpose. I could just do address OA less than equal to address OB and find out that, okay, I don't need to do anything. So now, how do we make sure that OB was placed on the stack before OA? The idea here is to determine an order for allocating non-escaping objects on the stack frames of methods using static analysis, and then use that order to reduce the overhead of heapification checks at runtime. If at all I can ensure this ordering, then I can just do address OA less than equals address OB, and my heapification check is done. I don't need to really walk the stacks to find out whether I need to heapify OB or not. So let's look at a simple example of that. If I have this original piece of code, now instead of zar, let's look at bar. I am passing A and B to bar at line number 11, and inside bar I am saying p1.f equals p2. I need to make sure that I have a stack order for laying out objects O5 and O6 on the stack frame of do. So if I construct points to graphs for these methods, in do I would say A points to O5, B points to O6. In bar, I would say, well, P1 points to some dummy object, some special object, let's say OP1, P2 points to OP2, and the edge I am creating here is a field edge from OP1 to OP2. Okay, that's the points to relationship I'm creating in bar. If I combine these points to graph, if I perform an interprocedural analysis, I can figure out that finally in do, O5's field F points to object O6. And based on this, I could determine that object O6 should be stack allocated before O5. Okay? So based on making a topological traversal here, let's say in the interprocedural points to graph of a method, we determine in what order should we stack allocate non-escaping objects. We make sure that in the VM, apart from stack allocating objects, we also stack allocate them in this particular order. And if this order exists, later on, if any store statement comes, the only thing I need to check at the runtime is a simple address check. That would be sufficient to determine if I need to stack allocate, if my stack allocation is incorrect, if I need to heapify a stack allocated object. Is there any question here? This is a critical point. we'll move to results and some more interesting discussion after this. I'll take, Pradeep, how much time do we have? Is it okay if I take 10 more minutes?
Oh yeah, sounds good, Professor. Yeah, it works.
Sure. Any questions here? All right. I hope it made sense to you. So here is the big picture, right? We are performing optimistic stack allocation and dynamic heapification for managed runtimes like Java virtual machines. We are basically statically I perform escape analysis. I use that escape analysis result. Along with that, I have these points to graph using which I can determine an order among the objects. I pass this list of stack ordered non-escaping objects to the VM. We use the Java virtual machine OpenJ9 in this case. And in the VM, I have an interpreter, I have a JIT compiler. So we need to implement this heapification check and dynamic heapification insertion in the codegen routines, as I said. And SOSA, there is stack order, stack allocation. I also need to modify the way a JIT compiler lays down objects on the stack frame of a method. Yes, Ramneet, you can take the question.
So you mentioned that hot code reloading may invalidate the results of the static analysis. Like, is it possible that it also invalidates the order static analysis, and then the address check is not sufficient anymore?
Good point, Ramdeep. So if the order is also invalidated, let's say, let's not use hot code. Well, hot code replacement directly cannot change anything in the static analysis, but let's say there is some malicious guy sitting behind who just modifies these, one of the security researchers or hackers, let's say, just sits and modifies my static analysis results. Or let's say statically my points to implementation was wrong and somehow I got a wrong stack order. What may happen in the worst case is the address check may not be sufficient, which means I should have a fallback that, okay, if address of OA is not less than equal to address of OB, instead of directly heapifying, if I want, I can go ahead and actually perform a check. So you could, if you have a safe fallback there, I mean, you would, in the worst case, you would perform more heapification. That's how I would summarize my answer. Make sense?
Yeah, thank you.
If I perform more heapification, of course, I would lose performance, but I still have soundness. Orders are not changing anything with respect to soundness here. That's one crucial thing to do. Okay. So a gist of results with this approach, we finally say, see, there is a big claim. We are saying finally we can stack allocate objects in a VM much more aggressively based on a static analysis. Now I don't need to perform forget about interprocedural data flow analysis and so on, context sensitivity, whatever. I don't need any analysis in the JIT compiler, let's say. I can just use static analysis results directly and allocate objects on the stack. So we found that we were able to use our approach and allocate for a large number of benchmarks, roughly 11x more objects on stack, 9x more bytes on stack. This means, of course, access time reduced significantly and then GC reduced significantly. We observed 25% fewer GC cycles. We also observed a 9.6% improvement in performance. You know, I have worked with Java even before, and in this space, you know, even 1 or 2% performance improvement over real world large programs is considered significant, and 9.6% improvement is really significant. And of course, the claim here is heapification will have to happen rarely. Only when something bad happens, you will have to do heapification. But now you have a way to safely use static analysis results, irrespective of any dynamism that may be thrown by the VM. Now, doesn't matter what code replacement, dynamic class loading, static analysis results going wrong, somebody modifying the result files, and even reflection, callbacks, nothing matters. Everything is safe. That was a big improvement we found. Of course, I told you that there are ideas and there were a lot of engineering, as well as there were so many ideas, novel ideas that came up here. So it was not easy to get it all done. You doing it in a VM across its interpreter, compiler required so many students. Adit is my PhD student here. Solai, Priyam, and Swapnil were my BTech students earlier. Vijay and Daryl were people from, Krishna was my advisor during my PhD. He was also part of our collaboration still. Vijay and Daryl are folks from IBM who helped us with OpenJ9, sometimes with technical questions and so on. Okay, what is happening? Can you help us here? And so on. So it required a lot of effort, a lot of cooperation from industry folks, and a lot of brilliant minds working together to finally finished this approach in a way that now it can be used in OpenGen NPL. This got published recently in PLD. So, well, I'll maybe just wrap up. As I said, 10 minutes, 5 more minutes are there. I'll just wrap up by saying this is just the beginning of dynamism. Java still is very much statically typed. There are languages like JavaScript, Python, R, so many dynamic languages that have many more dynamic features. A static compiler can do very less. Right? R, for example, is very interesting. It's not only dynamically typed, but it's also lazy. Lazy means you do not evaluate any argument until you try to refer to that argument in the body of a method. Okay. So interpretation is of course less performant in languages like these, but absence of types, laziness, reflection, all are bad for compilation, or all are bad rather for static compilation. So if I have a function in R which looks like this, f is a function that takes a parameter b and does b plus b. What can go wrong? You would assume that any static compiler or any standard compiler would be able to say that, okay, emit an addition instruction here, right? No, R is a lazy language and it is dynamically typed. So I can pass a function as argument to it. It has higher order functions. I can pass a function bad, and R provides a function to reflectively access something from its caller. So here I'm passing bad. Bad will be executed only when I refer to be in the body of the function f. And what will bad do? It will access its caller, which is f, delete the variable b from its activation record, which means that plus b, the second plus b, either it could be an error, it could probably try to add something to a function, or it could go and look up a global variable, so I cannot perform static binding. Even the addition there might be not the right thing to do, and a lot of other stuff, right? So it's very difficult to compile such languages, particularly in an AOT compiler. So we were working with the JIT compiler for R. I just want to tell that, okay, should we give up compiling F in that case? The answer is no. Maybe that bad function is passed to F only once in a while. Most of the times I pass an integer to it, or most of the times I pass a string to it, which if concatenated with itself returns a concatenated string in Java parlance, right? So most of the times maybe the function is not doing some unexpected behavior, but we still have dynamic types over here. Types are determined based on what you pass around. So what we in this compiler, what happens is we perform contextual compilation. We compile a method just in time based on what have you passed to it while I'm compiling. What have I observed to be passed to it? If I'm only passing integers, I can compile for 2 integers and give an optimized code. Okay. So this infrastructure in fact use LLVM finally. It performs these high-level optimizations based on promises, based on the knowledge of reflective arguments and so on. Finally boils down to LLVM bitcode and then executes it, right? We maintain multiple compiled versions of each function in this system, and assumptions about arguments are encoded as context. We dispatch to the most applicable version based on a context lattice. We form a lattice of context. For example, if I pass in an integer and next time I pass in a float, if I have versions available for both, the integer when I pass an integer, I can also use the float version if I have not performed any int specific optimization or things like that. Okay. So we dispatch to the most applicable version. Now, my claim is this is the way we could optimize a language like R. This is the way people would try to optimize languages like Python or JavaScript in the V8 VM and so on. So all this is too expensive, isn't it? We are talking about efficiency while using static analysis results in the JIT world. Here, just compiling multiple versions of a function, dispatching to the right one, all of it is too expensive, right? So for a JIT, but that's the only way to optimize such languages. What to do? So we came up with another approach that collects records rather versions of a function over a period of time, maintains a code repository where we optimize them further, we eliminate redundant versions. We do a lot of interesting things. It may look like a very simple box here, but we find redundant parts of context and so on, what part is really useful and so on. And we finally use them in or replay rather in the next execution of these programs. So this is another way of optimizing what happens in a complex JIT-based system, which we tried for the language R. And of course, I'll skip the details here. So the gist of the results, JIT compilers have overheads in the beginning when they compile the method. So you have these varmups. The red line here is varmups. The x-axis shows the number of iterations of a function. So initially when you run a program, as you can see, you have spikes. And similarly, we learned about speculation and de-optimization. So when you de-optimize, you will recompile a function, let's say in a new context. So you have this in-between spikes here, uh, maybe in some code here and so on. So there are these spikes which also slow down your program. Sometimes your applications are interactive, they may freeze and whatnot, right? So if you are able to reuse JIT compile code from previous runs of your program, which we did in this work, we can have fast startup performance and we can code switch during the optimization instead of recompiling, right? We also avoid context generalization, which is another interesting property. Instead of generalizing the context every time you see a new kind of argument, you can switch to the right version if you have compiled without incurring the overhead of JIT compilation. So this was published in UPSLA 2023 in collaboration with again several brilliant guys over here. So the idea of the whole of this talk was to both of these works to tell you that JIT compilers offer novel ways of optimizing programs, and they also perform. They also throw novel challenges or interesting challenges that are unsolved. There are some ways of solving some of those challenges which we are looking into at my research group at Compel IIT Bombay. We are performing these aggressive speculative optimizations in JITs using static analysis. We're trying to discover some new optimizations because now you have the power to take static analysis precision to the JIT world. So you can perform or you can create new, rather implement, I would say that's the right word, newer optimizations in the JIT that was not possible. You can save compilation effort and so on. We are also working on other JVM languages like Scala. Scala is a hybrid language, functional OO. So we are also performing some functional optimizations that are very specific to functional languages. You can parallelize some pure functions and so on. We are also making IDE plugins. The last bullet here says that some of my BTech students also tried to ease up compiler designers' life. They said, okay, it's very difficult for somebody to work with a compiler for the R language, such a complex runtime, right? So can we create novel visualization tools and debuggers for the compiler writers? We put in, I would encourage you to look at one VMIL work we had last year. We made it easy in some sense for anybody to pick up working on that particular VM and its JIT compilers, understand its IRs and so on. So we are doing a lot of this interesting work here, and I'm always looking for good students who can help us, particularly people from industry who have ideas and who can join us in this effort. And if you find any of this interesting, you can of course ask more questions if Pradeep says we have time. Otherwise, you can write to me over email, learn about our work. We will be very happy to talk more at any point of time. Thank you.
Yeah, thanks a lot for the interesting talk, Professor. Yeah, I think we are open to questions now. So,
yes, Srijan.
Oh no, that was a mistake.
Okay, Srijan has worked with Hugo. Oh, great. Yeah. Hugo worked with Lua JIT before working on R with us. He's a brilliant guy, I agree. Okay, Ramneet had asked some question. Could AOT compilers also make similar assumptions and have different versions of the function with runtime conditional branches? Yes, Ramneet, that's a very good point. So the problem, is this was in fact my end semester exam question recently in my course, in my code optimization for O languages course. So if you create these branches based on all the possibilities that can happen at static time, right? The problem is you will create lots of branches. You will insert lots of conditions. Whereas in the JIT world, you would create only those guards. You would put only those conditions that exist in the program at that point of time. Right? So I'll give you an example. I have a method called, let's say, x.foo. Now I put a condition here. Let's say if I may have 100 different possible foo implementations in the world in my program. Let's say, but the most common observed ones are class A's foo and class B's foo. So I can just check if the type of the receiver is A, dispatch to A's foo. Else, if the type of the receiver is B, dispatch to B's foo. Else, go back to the vtable mechanism, look up, find out which method is called. So I would insert this check for the only for the most common cases based on the runtime profile. If I instead wanted to do this statically, I may end up inserting either too many checks or not being able to determine which were the two popular receiver types over here. Okay. In the VM, dynamic class loading also gives me another interesting thing. If a class B has not been loaded in the VM till now, it means I can assume it doesn't exist. Okay. Dynamic class loading allows a Java virtual machine to assume that some parts of the program don't even exist. So it really becomes difficult, or in fact, it's impossible to statically figure out unless you integrate in some interesting ways the profiles from previous runs of a program. It would be difficult to figure out uh, more popular cases and optimize for them. We might end up inserting lots of guards, for example. I hope that answers your question.
Yeah, that makes sense. Yeah. Thank you.
Any other questions?
So I have a question, Professor.
Yes.
So what happens to interprocedural optimizations? For example, inlining, right? So if you inline a foo into another function, and you have these stack variables on them, do you also do the same thing like heapification on these stack objects?
Yes, good question, Pradeep. So since we have inserted these checks irrespective of whether you JIT compiled that code at a particular level or whether it was being interpreted, that means the check is there at every statement, irrespective of what part of the VM generated the code for that source statement. So basically, we attach it to we insert a new opcode in the JIT compiled code, and in the interpreter we attach it to the write barrier. And these checks are there irrespective of where does the code come from. So if foo calls bar and bar gets inlined in foo, that check might still be there. So basically, inlining won't affect anything. However, just to add on to it, we found that statically I could even generate conditions like if this method is inlined, then that object can be allocated on the stack frame of the caller. I hope you can see it. So one of my students is actually working on extending this idea such that conditioned to the inlining that may happen in the VM, I may be able to optimize even more. Instead of assuming statically nothing about method inline.
Okay. So would you also insert optimization remarks? Let's say like this function can be inlined or optimized away if certain conditions met. So instead of just like an address check or a value check, you can. Is it possible to do some remarks like optimization remarks check, something like that?
Correct. So we could say if at this particular bytecode index, this particular method is inlined by the JIT, and the JIT may do it with the speculation with profiling, right? So you're pointing to something which we are actually working on. We can definitely insert these checks or remarks as well.
Okay, that's great. Thank you.